Welcome back, everybody. It's Miss Maneely, and I'm sorry I can't be in class today. I know you all have your grade sheets and the test that we took last week, and I promise that we'll spend some class time next period going over the test. It's going to be really important that you guys understand how to complete each of those test questions because many of those types of questions are on your quarterly assessment. If you got less than a C, I think it's a really good idea for you to retake the assessment. And so if you want to come in to Bulldog Block on Thursday, I will dedicate Thursday's Bulldog Block to going over every question to make sure that you understand how to do it. And then you can begin with the retake next week. But I do think you guys are on your way. A lot of you did very well. Some of you are still struggling with the quadratic unit. And I do want to make sure that we clarify those points for you before the quarterly assessment because there are quite a few questions on the quarterly assessment that relate to quadratic functions. The quarterly assessment is worth 10% of your grade. It's the same assessment that every Algebra 2 student across the county is taking. So it's important that you guys are ready for it. Okay, so at this point you guys should have finished your warm-up. You have 4 questions or 4 polynomials, and you're asked to describe the end behavior of the graph for each of the polynomial functions by completing the statements. And it says to be sure to look at the leading term. So if you remember last class, we looked at graphs of polynomial functions, which do a lot of twists and turns. They're a little bit different than the parabolas that we were reviewing in the quadratic unit. They're all different shapes and sizes. And so it's important for us to kind of understand the similarities and some of the characteristics and see if there's any patterns that will help us identify some of the solutions. So if I take a look at number 1, it says f of x is equal to 3x squared minus x minus 4. The very first thing I want to look at is to see if that equation is in standard form. And because the highest exponent comes first, and then the next term is an x, and the last term is a constant, I know that the equation is in standard form. So I'm going to put a big box around the leading term. And if you remember from last class, we can determine the shape of the long run behavior. So if I were to look at this graph from really far away, it's essentially going to have 2 shapes, either a U shape or an S shape that goes up and down. If the exponent is even, so if the degree is even, so in this case my degree is 6, which means it's even. So that tells me it's going to be either a U going up or a U going down. The fact that my leading coefficient is positive, so I'm going to say is greater than or equal to 0, that tells me that my graph has to be going up. And so if my graph is going up, that means that on the left side of the graph, so that would be as x approaches negative infinity, since the graph is going up, that means that y approaches positive infinity. And if I look at the right side, and that's what this means, as x approaches positive infinity, that means look on the right side. What's happening to the right tail of the graph? This one is also going up, so that means y would be approaching positive infinity. We'll do the same thing for number 2. We have y is equal to negative 6x to the third plus 10x. So the first thing I'm going to do is I'm going to put a square around my leading term. It's odd, the exponent is odd, so the degree is odd, so that means it's going to be an s. My s is either going to be increasing or decreasing. And what I look at next to determine that is the sign. If the term in front, if that leading coefficient is negative, that must mean that my graph is decreasing to the right. So I know it can't be my first picture. Once you have a sketch, it makes it a lot easier to describe the end behavior. Because as x approaches negative infinity, that means we're looking at the left tail. So there's 2 ends to this graph that keep going forever and ever. But the first one, when x approaches negative infinity, means let's take a look at this thing on the left side. It's going up. So that means it's going toward, or y is going toward positive infinity. On the right-hand side, as x approaches positive infinity, my graph is going down. So that means my y values are approaching negative infinity. With number 3, we have f of x is equal to negative 4x to the fourth plus x to the 7th plus 2x. The one thing you need to notice about number 3 is that it's not in standard form because the highest exponent doesn't come first. So if I were to rewrite this in standard form, I'd want to make sure that my x to the 7th term came first. Then my minus 4x to the 4th and the plus 2x. When I circle my leading term, again, that's a 7, x to the 7th, tells me that the degree is odd, so I know it's going to be an S-shaped graph. And because the leading term is positive, I know my S must be increasing. So when I take a look at the left side of my graph as x approaches negative infinity, my y also approaches negative infinity. And if I look on the right side of my graph, this is as x is approaching positive infinity, I can see that my y is also approaching positive infinity. In number 4, again, this is not written in standard form. I have y equals negative x to the 3rd plus 3x to the 5th. I'm going to want to make sure that I put my x to the 5th, or 3x to the 5th, first, and then minus x to the 3rd. My leading term is 3x to the 5th. My degree is odd, so I know it's going to be an S shape. And because it's positive, I know it's going to look like number 3. It's going to be an S that's increasing to the right. And so if I look on the left side of my graph, it's pointing down. So I know that as x approaches negative infinity, so does y. And if I look at the right side, as x approaches positive infinity, I can see that y also approaches positive infinity. So that helps us identify what these graphs should look like from far away if we have the equation in standard form. There's not a ton of information we can get from standard form. I can't see where all the twists and turns are. I can't see where it crosses the x-axis. The only thing I can really tell is the general shape from far away. Is it an S or a U? And is it increasing to the right or not? The only other piece I could find would be like a number 1. My constant term does refer to the y-intercept. So that would really be the only thing. I'd know that this is going to be a U shape that opens up and crosses the y-axis at -4. But I can't really tell any details. Today we're going to be looking at the details, but we're also going to be looking at a different form of the equation. Today we're going to be looking at intercept form, or factored form. And this is very similar to what we did with quadratics. So we're going to be looking a little bit closer and looking at polynomials in factored form. So if you remember, with quadratics, we had things like x plus 2 times x minus 3. That would be factored form or intercept form. And you knew if x plus 2 was a factor, then x equals -2 was an x-intercept. And if x minus 3 was a factor, you knew that x equals 3 is an x-intercept. Well, with the polynomial, we're going to take it one step further. I could have x minus 1 and x plus 5 as factors. And I have 4 factors of x, 1, 2, 3, 4. If I were to multiply these all out, so if I were to FOIL over and over and over again, I would find that this is a function of degree 4. So what I could take from this, if you just extend what we did in the quadratic unit, I'd be able to say that a factor of x minus 1 means I'm going to have an x-intercept at +1. And x plus 5 means I'm going to have an x-intercept at -5. And since I have a function of degree 4, I can imagine then from far away it should look like a parabola either going up or down. And if I look all the way at the front of this function, the fact that there's not a coefficient there, so that means it's +1, that would indicate that from far away my graph is going to look like a parabola that opens up. That would be the long-run behavior. From far away, it would look like a parabola going up. If I were to look at it close up, and this is what we're going to be doing today, I could plot my x-intercepts. So I know I'm going to have an x-intercept at -2, at +3, at +1, and at -5. Let me extend my axis a little bit. And if my function has to look like a parabola from far away, then if I go to my leftmost x-intercept, I know that my function should be increasing to the right. And if I go to my rightmost x-intercept, my function should be increasing as well. So that must mean that my graph looks something like this. And that's what we're going to be doing in class today, is just sketching the graph of a polynomial function in in intercept form. So the intercept form gives us a lot of details that we didn't see when the equation was written in standard form. We're also going to take a closer look at the multiplicity of roots. You may remember that some quadratics we had double roots, and that occurred when the vertex was on the x-axis. And we're going to see that happening in this unit as well. We'll also look at what happens if there are triple roots. So when polynomials are written in standard form, we can easily determine the end behavior just by considering the leading term, and that's what we were doing in the warm-up. When we want to examine the polynomial functions up close, we can refer to this as the short-run behavior of the graph. It gives us a little bit more detail. In this activity, we want to examine the relationship between the factors of a polynomial function and its roots. So we're really going to be looking at the factored form of polynomials today. And there's a theorem. It's called the fundamental theorem of algebra. If you guys remember theorems and postulates from geometry. The fundamental theorem of algebra states that a polynomial of degree n must have n roots. Remember how we said quadratics? Because it was an x squared, it was of degree 2, we had to have 2 roots. Either both of those roots were real, or both of those roots were complex, or maybe we had one real root, but it was a double root. So either way, there would be 2 roots to every quadratic function. Well, if my function's cubic, that means there must be 3 roots. If it's quartic, there must be 4. If it's a 7th degree polynomial, then I will have 7 roots. Some of them may be real, and some of them may be complex, just like we saw with the quadratic unit. So what you're familiar with is this first example. I've got a graph of a parabola, and I can see that it crosses the x-axis at -1 and +3. And we spent a lot of time writing equations for parabolas, right? We said then that means that y would have to equal, and this would be our intercept form. If you remember, a times x minus p, whoops, I'm not sure what happened to my calibration there, times x minus q. That was our intercept form for our parabola. Well, if I know the values of p and q are -1 and +3, I can rewrite this as x plus 1 times x minus 3. And then I have to figure out my a value. And in this case, since my parabola is opening up, you would expect the a value to be positive. I can also see, sorry, my board's not calibrated anymore. I can also see that my vertex, if I were to go up 1 over 1, I'm landing on the graph again. So that must mean that my a value is a positive 1. All right, let me try rewriting this. I just recalibrated my board, so that should be x plus 1 times x minus 3. So that should look a little bit nicer. So if you notice the next graph, now this is a polynomial. It has a couple twists and turns. If you think about it from far away, if you think about like the long run behavior, you can see that this is an S-shaped graph, which should lead you to conclude that the degree must be odd. And because it's increasing to the right, the leading term must be positive. If we take that a little bit further and start looking at the x-intercepts, I can see that I have an x-intercept at -1, an x-intercept at +1, and an x-intercept at 3. So if I wanted to write this polynomial in factored form, I'm going to do the same thing that I did with quadratics. That x-intercept at -1 is going to correspond to a factor of x plus 1. And the x-intercept of +1 is going to correspond to a factor of x minus 1. And the x-intercept of 3 is going to be x minus 3. Then the only thing I have to really consider is what my leading term is going to be, or what my leading coefficient is going to be. And at this point, let's just assume it's either +1 or -1. And we already determined by looking at the long run behavior that it must be a +1. All right, so we want to relate the degree of a polynomial to the zeros of the function. Every polynomial of degree n has exactly n zeros or roots. And when those roots are real numbers, they're going to correspond to the x-intercepts of the graph, just like they did in quadratics. Well, we talked a little bit with quadratic functions about how sometimes our roots are double roots. And that's going to happen when our x-intercept happens to be a turning point. And what I mean by turning point is that the graph changes direction. A turning point is going to be either a max or a min. It's going to be like the vertex to a parabola. So a turning point means that the graph is changing directions, and that would mean that that point is either going to be a maximum or a minimum. With quadratics, there was only one. Either we had a maximum or a minimum, and that was the highest or lowest point on the graph. What we're going to find with polynomials is that there could be several maxima. We call them relative maximum, or maxima, or relative minimum, or minima. So if it's a turning point on the graph, then that represents a double root. If it's what is called a point of inflection, which is what this is right here. Sorry, my board's somehow not calibrated again. So if the, try that again now. This is what we call a point of inflection. And this is where the graph changes concavity. So if you look at the beginning of this graph, if you look on the left-hand side of that point, you can see how the graph is sort of curved down. That means the graph is concave down. But if you look on the other side, beyond the point, you can see that it changes concavity and suddenly it's concave up. So the point where the concavity changes is what we call a point of inflection. And if the point of inflection occurs on the x-axis, that means the x-intercept is a triple root. And so when we start writing it in factored form, we'll want to remember that. This is referred to as the multiplicity of roots. So polynomials can be expressed in standard form like we saw last time, or in factored form like I showed you in the last example. And the factors of a polynomial often relate to the x-intercepts. So if I have an x-intercept at -2, that means the graph crosses the x-axis at -2. When I write it as a factor, it's going to be the quantity x plus 2. And that's where I put it in parentheses. If the x-intercept is at 3, that means I'm going to have a factor of x minus 3. Well, if x minus 2 happens to be a double root, that means that the quantity x plus 2 occurs twice. So I square it. If x equals 3 is a triple root, that means it occurs 3 times, and I would have to cube it. And so we'd put all of that together to be able to write an equation in factored form. So let's take a closer look. In fact, let me make this view a little bit bigger so you can see it a little better. So in this example, you see a polynomial. You can see that it hits the axis, or hits the x-axis, 3 different times. And at each of those points, it looks slightly different. So at the first point, this is when x is 1, do you see how the graph just passes straight through the point? It doesn't change at all. It's decreasing the whole time. It's not changing concavity. It's not changing direction. It just passes through. In fact, if you were to sort of block it off, if you were to sort of zoom into that, it would almost look like a line going through the point. That means it's a single root. So in this case, if x is 1 is my root, or my x-intercept, if it passes straight through, if the graph just passes through like a line, it's considered a single root. And so if I write it as a factor, I'm just going to write this as x minus 1 and put that in parentheses. If I take a look at number 2, at the second root, again, it's going to cross the x-axis at 2. I can see that my graph is increasing, 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 and then as it hits 2, it begins to decrease. So this is an example of when it changes direction. So x equals 2 is going to be my root. Because the graph changes direction, this is what we call a turning point. Okay, it's a maximum or a minimum. So that might be another way for you to remember. And in this case, it's a maximum. So if it's the vertex, for example, then that means it's going to be a double root. And when I write this as a factor, I'm going to write x minus 2, and I'm just going to square it because that means the factor occurs twice. If I take a look at this last root, it crosses the x-axis at 4. And if I take a look at what's happening on the left of this, I can see that the graph is almost concave down. And then on the other side of 4, I can see that it's concave up. So the graph passes through 4, but it changes a little bit. It was concave down, and then it becomes concave up. This is what we call a point of inflection. And it's a little bit different than the first situation that we saw, we can see that it's changing concavity. That means it's a triple root. So where x is equal to 4 is a triple root. So when I write this as a factor, in parentheses, I have x minus 4, and I am going to cube that. Sometimes when you're looking at a graph, especially if it's very, very steep, it's hard to tell the difference between a single and a triple. So if you've graphed a parabola, if you've graphed a polynomial and you're finding it hard to determine if it's a single or a triple, you can always zoom in. So if I wanted to now put all of these pieces together, so here is my function, I want to write it in factored form. Well, I just figured out each of the factors by examining the x-intercepts and the behavior of the graph at each of those points. I can simply put this all together. I can call it y or f of x or whatever I want to call it. And I'm just going to put my factors together. Remember, with factors, we're multiplying. The only other thing you'd want to pay attention to is that leading coefficient, that a value that we saw with parabolas. If my graph is increasing to the right, then I know this number has to be positive. And so I'm just going to put a positive 1 just to reinforce that. Obviously, if it's positive 1, you don't actually need to put a number there. But that's one good way to remember. So basically what we've done is we've just taken this crazy looking graph and we've actually come up with an equation to model it. Let's do another example. So here's another function. And the first thing we want to do is identify the x-intercepts and the multiplicity of the root. So I'm going to look for all the places that the graph either touches or crosses the x-axis. So that's going to be here, here, and here. And let's go ahead and identify the x-intercepts. I've got one at 0, one at 2, and one at 3. Let's think about the multiplicity. If I look at the first part, if I look at that first x-intercept, notice that the graph passes straight through. It doesn't change direction, and it's not changing its concavity. That means that it's a single root. If I take a look at the second x-intercept, again, I see the graph passes straight through that point. It doesn't change direction or concavity, so this is also a single root. The last point, however, I can see my graph was increasing, and then it starts to decrease after it passes 3. That means it is a turning point, which indicates that it is a double root. So if I put the x-intercepts together, I would say that x equals 0 is a single root. I would say that x equals 2 is a single root. And I would say that x equals 3 is a double root. And we can go ahead and put that in factored form in letter C. So if x equals 0 is single, I can write this simply as x minus 0. And if you want to put to the first power for now, you can. If x equals 2 is single, that means my factor is going to be x minus 2 to the first power. And if x equals 3 is a double, that means I'm going to have x minus 3, the quantity squared. We also have to consider that leading coefficient. What must be true about the leading coefficient if my graph is pointing down to the right? The a value, that leading coefficient, must be negative. That's the only way that my polynomial will decrease to the right. The leading coefficient must be negative. So I'm going to go ahead and put a negative there. Now, there are other ways to find the exact value of a, but in all of these examples, we'll assume that that leading coefficient is either a positive 1 or a negative 1. And the last thing I'd want to do is just simplify this a little bit. For example, x minus 0 is just x. And I don't need to put that first exponent. I can just leave it as negative x times x minus 2. I don't need to raise it to a power of 1. And then the last factor, which would be x minus 3, the quantity squared. And that would be an equation in factored form for that graph. Okay. Another important characteristic of graphs of polynomial functions is that they have turning points, and again, that's where the graph changes direction, and they correspond to either a local or relative maximum or minimum value. Here's another characteristic, though. The graph of every polynomial function of degree n has at most n minus 1 turning points. So what that means is if there are 3 turning points, the degree has to be at least 4. If there are 5 turning points, then the degree would have to be at least 6. If there are 18 turning points, the degree of my polynomial would have to be at least 19. So the degree has to be at least 1 more than the number of turning points. And vice versa. If you know the degree, if you subtract 1, you'll get the maximum number of turning points. It's not a perfect fit. It's an inequality. So if we take a look at the first example, you're given an equation. F of x is equal to negative 3x to the 5th plus 2x to the 3rd minus 4. Now I will say in this case when we're talking about the turning points, they don't have to turn on the x-axis when you're associating them with the degree. So if we think about the degree of this polynomial, the degree is 5. And that must mean then, if the degree is 5, how many roots would there have to be? The number of roots needs to match the degree. So there must be 5 roots. Some of them may be real, some of them may be complex, and we'll get into that a little bit later. But if the degree is 5, there needs to be 5 roots to this function. And then if I wanted to look at the graph, I could also look at the graph in terms of the number of turning points. The maximum number of turning points is always going to be 1 less than the degree. So there would be, at most, 4 turning points. And this is important. Knowing this relationship is important if there are imaginary roots. Because if you're graphing a function and all you see are the real roots, you need to know if imaginary roots exist. And you can tell by the number of turning points. So if we take a look at the next example, this time I'm giving you a graph. And the question is, how many turning points are there? Well, if I follow my graph, I'm just going to trace it with my pen. So I'm increasing, increasing, increase, and then here I'm turning around. So there's 1 turning point. And if I turn around again, that means that there are 2 turning points on this graph. One of those turning points occurs on the x-axis. So that means that the x-intercept associated with that point, x equals 2, is a double root. And so I could write that as x minus 2, the quantity squared. And if I think about that x-intercept there, that tells me that x equals 0. And the factor associated with x equals 0 would be x minus 0, or simply x. So if I can see the graph and I can see the x-intercepts and I can see the multiplicity, it's easy enough to write the equation in factored form. But if I want to understand it in standard form, sometimes these other characteristics are important. So again, how many turning points are there on the graph? There are 2. So what does that mean about the minimum degree of the polynomial? It must be at least 3. And that sort of makes sense if you think about it. If I have 1 root here, and this is a double root, so this is single, so 1 root here, and then this is a double root, when you add them all together, you have 3 roots, or at least 3 real roots. So my degree would have to be at least 3 in order for that to be true. Now, there are times when there are imaginary roots, but we'll take a look at those examples a little bit later on. So I've already written the equation in factored form. If I wanted to write it in standard form, I can see that this must be an odd degree, right? If my degree is at least 3, it means it's got to be an odd degree. So if I look at my answer choices, I can automatically eliminate my x to the 4ths. And then I have to choose between a negative x to the 3rd and a positive x to the 3rd as my leading term. Since this graph is going up, I know that the only possible choice would be the last one, where x to the 3rd is my leading term. And again, if you look at your factors, this x is to the first power, and then this x here is being raised to the second power. So when you add them together, it makes sense that x to the third, or the degree 3, would be the degree of the function. Okay, you're going to do a little activity with your partner. And basically, you're going to have a bunch of little graphs, and then you're going to have a bunch of factors. Some of those factors represent a single root, some of those factors represent a double root, and some of them represent a triple root. And your goal is to basically write out an equation for each of the graphs by using the factors. So it's a sorting activity where you're going to match everything up and then hopefully be able to write the equation in factored form. So go ahead and press pause on the video and go ahead and complete the activity with your partner, and then we'll wrap up in a little bit.